Today we will present you ODS Paris meetup. This meetup will be organized in 3 parts. First part will be presentation of winning solution for TReNDS Neuroimaging competition. Second part will be a question answering session with Nikita. And the last but not least part, it will be the networking event with Icebreaker platform that we encourage you to discover with us. Let me say the word of gratitude for our organizers. Me, Anton, with Evgeny and Oля, brought to you this new format of ODS Paris online meetups. And without further ado, let me introduce to you our guest speaker, Nikita CHURKIN. Good evening, Nikita. So, today Nikita will present you his winning solution for the Kaggle Neuroimaging competition. Nikita, the floor is yours.
What's the plan for today? We will talk about our background, task, a little summary, feature engineering, training methods, some progress chart, and kind of sketch of top approaches. So what for the background? I participated in this competition with my friend Dmitry Simakov. We are both hold bachelor degrees in economics, master's in computer science, and additionally I have a second master's in mathematics. Now I work as data scientist at Sberbank. Dmitry used to work with me at Sberbank too, but now he's a DS in a small computer vision startup. So let's get started. Before, I want to give you a little disclaimer. Actually, there's a lot of details and nuances in preparation of competition data, our solution, other top solutions. So we have a time limit. It's impossible to describe everything in one single talk. So I want you to check out some useful sources like competitions data page, trends post-competition slides. It contains like explanation for how data was prepared, how targets were prepared, our winning discussion post, our code is on GitHub, and a useful video I say of functional MRI data. It is really helpful to understand how to preprocess competitions data. So what's the problem? What do we have? The problem is to predict targets using MRI scans and extracted features. We have 5 continuous targets: person age and assessment values from 2 domains. The names are age, domain 1.1, domain 1.2, etc. By now, from post-competition slides, we know that assessment values, domain 1.1, domain 1.2, are actually a combination of 9 variables in 3 domains like behavior, lifestyle, cognition. But you can look at, you can view them like some sort of anonymized continuous variables. Public-private split was 50-50, almost 6,000 objects in train and test. A metric for this competition is weighted normalized absolution error. So look at the formula right here. Normalized error, normalized absolute error is just basically Maya, but you replace n in this part of the formula with some of the targets. And you have individual losses for every variable, age, domain 1.1, etc. Then you just use convex combination of individual losses with following weights to calculate the final loss. Here you can see that predicting of age is actually a little bit more important than predicted then prediction of domain 1.1, domain 1.2. And we had only 3 submissions per day. These slides gives you basic understanding of what data we have in this challenge. So first important source is preprocessed fMRI scans, functional MRI scans, 53 3D spatial maps for every person, for every object. Actually, fMRI scans in this competition is not like raw fMRI scans, as we understood. Sponsor have a very complex and sophisticated pipeline of preprocessing raw scans. You better check post-competition slides. But as I understand, they receive series of 3D fMRI images. Then they remove effects of head moving and time series component, and they perform dimensionality reduction via ICA. Second source of the data is tabular data, features extracted by organizer. Tabular data is ICA components of structural MRI data, aka loading data, and FNC matrices or connectivity matrices. You can view them as some correlation between different brain sectors for a particular person. So interesting feature of this competition is dataset shift between train and test datasets. We know that some test objects were obtained with use of different MRI scanner or site. So train set corresponds only to site 1. Test set corresponds to site 1 and site 2. So all site 2 objects are in the test set. So we can use them directly for training. But sponsor gave us some hint. Approximately 500 of IDs of site 2 data were revealed for us to calibrate our models and come up with some sort of combat tactics, how to make datasets closer. And actually, they are very interesting. There's very interesting line from the data description. I want you to remember it. Side effects are form of bias. It's actually a very good hint. When we started this competition, we decided to believe in the following hypothesis. We believe that distribution of target data, this joint distribution of target plus dataset are unchanged for site data, but distribution of data itself in test is different. So it looks like on the picture on the left. By now, from post-competition slides, we know that approximately 17% of total amount of samples were actually site 2 data. So it's approximately 1,000 of points in public test and 1,000 of points in private set. So what is the summary of our approach? At first, we created a diverse bundle of different features. Let's call them feature blocks. The most important features were raw data, like IC components from loading file. It's basically that source. And it was important to extract PCA features from 3D fMRI scans. For test set, we calculated offsets to minimize difference in train and test distributions. I will explain it a little bit later. So we have some data that we know is from site 2 distribution, so it's actually natural to come up with the idea of classifier, how to figure out more hidden site 2 objects in tests and do something with them. And as final step, we trained many linear kernel-based models and also one tree-based model, regularized greedy forest. Here you can see the link for corresponding paper. This slide illustrates one example or sketch of example for fMRI data. So one feature had the following shape, and you actually have 4D data because you have 3D scans and 53 spatial maps or features or channels. Our main feature block is incremental PCA on 3D fMRI pictures. How you can calculate it? You have 53 spatial maps for every image. Split them into 6 groups. 10, like 5 groups by 10, 1 group by 3. Inside one group, you concatenate maps and flatten them into one long vector. And then you just apply scikit-learn incremental PCA with 200 components in batch size of 200 on top of them with partial fit method. We have 6 groups in total and 1,200 PCA features as a result of this operation. So PCA features were like the best features in this competition, and we believe this was the main source of our success in that case. You could use dictionary learning from scikit-learn 2 instead of incremental PCA on fMRI data to get the same kind of features. DL features were actually worse in terms of quality than incremental PCA features, but we added them for diversity. It is important to notice that PCA and DL features you're fitted on train plus test data. And we designed some simple additional features for diversity, like statistics, mean, STD, quantiles, inside each feature channel, and similar statistics for connectivity matrices. Let's talk about dataset shift. Biases for the features and predictions. I want you to recall this statement: side effects are a form of bias. And look on the left picture. Train and test, or train or site 2, it's unimportant. Distributions plotted against each other. You can see that you actually can add some numbers to, like here. And obviously, distributions are not perfectly matched because of addition of some number, but we can see our models, especially linear models, can get a huge boost of such operation. And in fact, it was a very important step in our solution. And our cross-validation was had just perfect correlation with leaderboard score, with private part and public part. So basically, additive bias to different columns in tail set to make it closer to train set. this operation was performed. We used Kolmogorov-Smirnov statistics and differential involution. So we tried to minimize Kolmogorov-Smirnov statistic value between train column and train column plus particular bias. We calculated biases for the test as a whole and separate side 2 only. So we know that test comes from side 1 distribution and side 2 distribution, but test side 1 distribution was different from side 1 training distribution. So bias is actually important for all tests, not only side 2 data. And you could apply the same logic to the predictions, just match side 2 and side 1 distributions of predictions. The next kind of natural step is to come up with side 2 classifier, figure out more side 2 points, and perform more aggressive offset trick to new points. This slide just explains some features, model and training procedure for our classifier. So the base of our classifier is raw ICA structural MRI data, connectivity features, and PCA, standard scalar, both for train plus TS data. The main model is regression, elastic net. Training was boosted with the help of pseudo labels inside the training folds. The following scheme just illustrates previous slide. So you have train fold, you fit elastic net, predict test, make hard labels, concatenate train fold and test spreads, fit model again, predict test, and val. The next step of our pipeline is creation of so-called scores. So scores are basically just out-of-fold predictions that are learned on the data of only one data source. It's a very popular idea in banking or risk modeling when you use like 3 different or maybe more, 3 different data sets, put linear models on top of them and combine them via some linear model. But in this competition, we are not restricted to use only linear models, and we used some classical models like RICH or OMP, plus one tree-based model, regularized greedy forest. We designed 5 separate scores: connectivity matrices, for connectivity matrices, connectivity aggregations, image statistics, PCA features, and dictionary learning features. So we had like scores for every target plus data source. We have 5 different targets, and domain 1, 2 was extremely hard. So
we verified that stream will be continued normally, and I invite Nikita to continue from the place where he finished. Nikita?
So we are live.
Yes.
Yeah? I was explaining how we predicted each target. So domain 1, 2. For this domain, it was extremely hard to come up with better models, better than median prediction. So we decided to stick with simple median prediction for this label, and it worked perfectly well. Some target values more complicated than others. Domain 2.1 and domain 1.1 were more complicated. in terms of higher loss on cross-validation. So we decided to use more simpler staking scheme for domain 2.1 and domain 1.1. And the age label and domain 2.2 label were quite easy. So we use more advanced ensemble scheme for them. And the final ensemble contained more models and more layers in case of age. For every label, domain 1, domain 1.1, domain 2.1, domain 2.2, plain blending was used. So we train corresponding models on different data sets and then just blend the outputs in weights in 0.1 segment to minimize normalized absolute error. And for figuring out which ways we should use, we use custom differential evolution optimizer of our out-of-fault metric value. For the age, we applied one additional layer of stacking before blending. We have a GitHub repo where you can find boring description of every data set, every target, every model, every target data set compilation that we use. And it is very time consuming and boring to just giving the list of all combinations here. So I'm going to show you only stacking scheme for age. So remember that we have some future blocks plus scores. MLP here receives only one data set from here. Regularized greedy forest receives only one data set from here, and so on. So we have 7 models on different data sets. Then we put Bayesian enrich on top of them, and one more copy of regularized greedy forest. And the outputs are just blended with weights that we found by hand. This slide illustrates our progress chart. Actually, our path to the top one was pretty straightforward. I personally was like 99% sure that we will win this competition, even, and we will get good score even on the private part. Here you can see like every powerful trick or magic we found in this competition, like biases, bias trick for tests and side 2, PCA powerful features, staking with linear models, staking with all models, and the post-processing. So we spent like maybe 10 days of like intense participating in this competition. Important findings: we used a large stack. We actually staked 7 different seeds in the last day of the competition. In the next slide, I will give you some overview of tricks from other top participants, and you can notice that large stack is pretty important in this competition. But as far as I understand, that large stack can be relaxed and still be capable of generating score for the first place. And actually, you can have a gold medal with only one model. So the recipe for this place is actually use simple elastic net plus PCA futures, do offset trick, and you will end up on like 10th or 11th place. So it is pretty funny. I can explain every good solution in this competition. So I designed 2 slides with like top 7 best teams solutions in this competition. So basically we can see that using fMRI data is essential for getting gold. So on a day I used 3D ResNet as feature structure and then staking. Some participants used deep learning models like transformer or graph isomorphism networks, more simple networks like one-dimensional CNNs. Some participants have domain knowledge and they constructed good features and use staking too. Almost everyone, or maybe the most of the teams, use some side to normalization or sample weighting or classifier. So it was, like I said, it was very natural idea to come up with some methods to kill this dataset shift. Guys from the 6th place used autoencoder on top of spatial maps and then stack. So I believe I told you pretty much the core of our solution. Here you can see our contacts. You can reach us if you have some questions, so ask them now. Anton, I'm ready for questions.
So thank you, Nikita, for this great presentation. Once again, congratulations with the first prize in such a difficult competition. Right now, we will make a small Q&A session, and then we will continue with the networking part on Icebreaker server. So let me start with my question. So you introduced several other solutions and you described them a little bit. What can you say about what was the main competitive advantage in your solution in comparison to other?
I believe our PCA features is like the most powerful variation of features you could have extracted from functional MRI data. It's one component, and second, I believe that Sci2 bias trick is actually the best trick for fighting with dataset shift. So we kind of found 3 magics, as I described in this competition: staking, bias correction, dataset shift fighting, and asserting features. And I believe that our staking scheme wasn't the best, so we actually didn't tune our models a lot, but biases were quite good, and PSA features are just crazy in the terms of final quality.
So thank you for this.
I guess we did better in 2 points of 3, like that.
Mm-hmm. Thank you, Nikita, for this developed answer. And if you don't have other questions, I will ask some basic stuff. So you have a lot of model in your staking. What kind of hardware you used to perform computations?
Hardware was, I say, important in this competition. We used 2 machines, both with Ubuntu OS. Actually, I gave a try. I tried different models on different computers. So I used in Ubuntu, Windows, and Mac, but we ended with using just Ubuntu's two computers. GPUs were not important in this competition. We basically used scikit-learn plus package for regularized greedy forest and some other basic packages that doesn't involve GPU computations. CPU, I believe, isn't important too. Of course, better CPU is better. You can learn faster, calculate faster, but I'm not sure it is essential. And essential part is amount of memory. We have 64 gigabytes of RAM on both machines. So RAM is important for incremental PCA creation and dictionary learning creation. For staking, I believe it's enough to have like 32 gigabytes, maybe less. And disk space, free disk space was important too. I believe the final space of models, futures, some intermediate models is up to 500 gigabytes of disk space. So it was RAM and free disk space are essential. Other things are not important.
So that was an interesting overview of your hardware. We have next question from Dmitry Ukrainsky. As he understands, you spent only 10 days of hard work for approaching the best result. Do you have a special strategy for participating in this competition in the beginning? So what was your strategy from the beginning?
I used to spend a lot of time on competitions, and for a long time I believe that is the best strategy to start right at the start of the competition. But now I'm not sure is it optimal strategy, and tend to start competitions before like 1 month or less before the end. So I think it is more time consuming, it is more difficult. So basically I spent like maybe 15 hours per day in the last days when we staked models, when we try to figure out new tricks, do some learning of new models, but it was quite effective, I would say. So I think that is more optimal to start before like 1 month in the end, but it depends on computational difficulty of the competition. If you have a lot of data, some deep learning competition, it would be painful to start late. And in the tabular case, it is fine, I suppose. But everything it depends on difficulty and the specific features of the competition. So they are not like one universal strategy of timing.
So thank you for the answer. When you use neuroimaging, sometimes you can draw interesting pictures and maybe have some insights from them, like in 3D brain, as you shown in your slides. Was this really important in this competition, or you just used some plots, looked at some distribution? So what was the main part of your exploratory data analysis?
I'm not sure it was important here. I'm talking about fMRI scans. So we just use some PCA extraction. And I personally didn't do some extensive analysis of images. And for tabular data, it were like basic plots, some distributions like that, when you can figure out the differences between train and test, or between train and site 2 data. So it just standard, I believe it's just standard package of tabular techniques for tabular data sets. And fMRI data were too complex to figure out some insights based on the picture of brain. So it is quite complicated. How you understand the age of person if you see this type of picture, and also has like 53 feature channels. So it's too complicated, and I believe maybe for some experts or people with domain knowledge, it was important and helpful to check all spatial maps, for example, but not for us, I suppose.
Nice. So let's wrap up our question answering session with 2 questions, not about competition, but a little bit more personal. So the first one is from I. Why did you put Hobgoblin on the avatar?
Actually, I like Spider-Man 1994 cartoon. It was like my favorite cartoon from my childhood. So basically, I like this villain. So it's all.
Nice, favorite villain. And the second question from Alpha Olish, for how long are you doing Kaggle competitions?
Maybe like 3 or 4 years, including not only Kaggle but other platforms. So sometimes I put more time on other platforms because I see any interesting problems on other problems. But now I suppose Kaggle just gathers the most interesting tasks, and other platforms doesn't seem to be interesting like Kaggle. So basically 4 years, 3 years.
Nice, you are really experienced Kaggler. So thank you, Nikita, for this presentation. If you want, you can join us at networking part. So we will finish our Open Data Science Paris meetup, and the next part will be at another platform which is called Icebreaker. You will find the link in the description down below or in the chat.